All right, well, welcome everyone to our weekly Wednesday webinar series. This course is approved for 1 hour continuing education units, GBCI, AIBD, Passive House Certified Passive House Consultant, as well as AIA Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. This course is brought to you by the Green Home Institute. My name is Brett Little. I'm the program manager here at the nonprofit. What we're going to be focused on is the new Passive House 2021 standard and the Source Zero standard as a part of that. So kind of two different standards in one, and then how those fit into briefly into the LEED program. And before we get started, a huge thanks to our top tier sponsor, Mitsubishi Electric. Mitsubishi provides all your heating, cooling, and filtration needs all in one system. Today's low-load homes require right-sized equipment that most systems, especially gas-fired, cannot meet. Mitsubishi has low-load, high-efficient heat pumps that dehumidify and cool in the summer and work in reverse to heat in the winter. Going ductless reduces costs and makes it easier to meet Energy Star version 3 and LEED certification. Ductless mini splits can now be hidden in many different ways to meet your client's needs, and ducted systems can be used as well. Ducted systems are hidden behind the walls to ensure beautiful space and can be retrofitted in place of a furnace in existing single-family or multi-family. Set your system to dry mode when cooling is not needed as much to help remove excess humidity. Each room of a house can be customized comfort while still being all electric and energy efficient for clients with different needs and only heat and cool rooms that actually need it. Hyperheat ensures an efficient heat delivery down to -13 degrees, and backup strip heaters can kick in during the rare but coldest of cold days. Take my word for it, the other week when everything had just happened, my system was still keeping us warm. I'm still alive. I did not freeze to death up here in Michigan, and they work great. From a multifamily and commercial standpoint, centralized variable refrigerant or VRF systems work on large projects looking to serve whole buildings. So go learn more at Mitsubishi Comfort.com. And then thanks to our second tier sponsor who just came on board today, Great Lakes Passive House Supplies offers a simple concept: frost protected shallow foundation, ICF, and air heated radiant floor systems. The radiant heat circulates warm air through a network of air pipe being cast into an insulated monolithic concrete slab foundation, which is custom engineered to building specifications. Air is the only heat transport medium traveling through a closed circuit, transferring all of its dissipated energy in an even, gentle, silent, safe, and leak-free manner, far superior to hydronic radiant systems. The GeoSlab insulated concrete slab provides foundation that optimizes thermal mass for heat storage and delivery throughout the building in a controlled manner, providing comfort economically. Contact Eldon over at totalicf@gmail.com. All right, and my computer is locking up, but that's okay. We'll keep moving forward. So if you can see my screen or not, real quick, before we get started, Passive House does fit into LEED, and the biggest part, of course, is the energy and atmosphere section. And in this section, there is an actual ruling in the addenda that talks about, under the LEED B4 rating system anyway, that you can capture roughly 20 points automatically by being Passive House certified. Now, I will say that ultimately we see, especially nowadays, Passive House projects pretty much capturing all of the LEED points, whether it's in multifamily V4 or single family V4.1. That's not a guarantee, like this addendum is set up, but for the most part, what you're going to need to do and what you're going to hear about in a second is pretty much going to score a majority of your energy points, which is about roughly a fourth of all the credits you need in LEED, right there taken care of by Passive House on the energy side alone. Now, Passive House is not just an energy efficiency standard, and you're going to hear a lot more about that, but how it fits into LEED is that it requires Indoor Air Plus certification, and Indoor Air Plus certification basically covers many of these requirements in the environmental quality section of LEED: ventilation, combustion venting, garage pollutant protection, radon resistant construction, Air filtering, environmental tobacco smoke, compartmentalization, sealed units, very important to keep air we breathe from going in other places, especially nowadays, and enhanced ventilation. All of these items are taken care of under the Indoor Plus program, which is covered under Passive House now for the US version. And so there, again, even more points taken care of there as far as your prerequisites go, and a couple points in air quality. Really goes a long way and shows that the LEED and Passive House program go hand in hand. So we'll talk a little bit more about that later, but now I'm super excited to introduce our speaker here, Lisa White. Lisa has been with the Passive House Institute US, or FIES, since 2012, and currently serves as the Associate Director. She is also an instructor for Certified Passive House Consultant and WUFI Passive Software trainings. White holds a degree in Environmental Sustainability with a minor in Architecture from the University of Illinois at Urbana-Champaign, and she is currently pursuing her master's in Energy Engineering at the University of Illinois, Chicago. White works on certification training, WUFI passive development, and is a member of the FIES technical team. She also provides consulting services on static and dynamic energy modeling in WUFI passive, therm modeling, and project planning specific to passive house building principles. She has presented at numerous conferences, including Greenbuild, ASHRAE, FIES North American, and the Affordable Comfort Institute. And I'm really excited. I think this is your second time, maybe third time here with us, Lisa. So welcome back. And at that point, I'd like to hand it to you. So please take it away. Thank you.
Thank you, Brett. Let's see. Okay. We up on the right screen?
Yep, you're on.
All right. It's hiding my webcam over here. Okay. Welcome, everyone. Let's get this going. Okay, so as Brett mentioned, we're going to be talking about Passive House today. We're kind of going to go all over the spectrum here, starting with just kind of the basics of what is a passive building, what are passive building principles, and then how are those used to create or define a standard, a certifiable standard, and then a little bit more emphasis on how you use that standard to get to zero, which is our FIES Zero program. I don't know if Brett mentioned it, but I'm happy to take questions throughout, put them in the chat. My colleague and our project certification manager, James Ortega, is here to join and help answer some questions in the chat as well. So we'll take questions at the end, but also throughout if you guys have them. Okay, so I think Brett mentioned this. It earns 1 CPHC CEU. I'll keep going here. Okay, so before I dive in, I just want to briefly touch on what FIES does. So we are a standard setting body that creates standards for building certification. So in the top left, you can see our 2 levels of building certification, which you will know all about after this webinar. We also certify data products that go into buildings. So you can see a Windows certificate there. We work with an energy modeling development team, Fraunhofer Institute of Building Physics, to develop a compliance tool, which you guys will also see, WUFI passive modeling software. And we also train and certify professionals. So we have 4 different professional designations: certified consultant, certified builder, rater, and verifier. And I'll talk through later on how those fit into the building delivery and certification process. Okay, so just to start at bare bones here, this was the first graphic, I don't know how many years ago now, that when I was introduced to passive building, this is what I was shown. So what is a passive building? Each of these items, right, is accomplishing the goal of holding a liquid or something. If you put something warm in the solo cup, it's going to cool off, right, or something cold. It's not protected, shielded. It's not quite as thoughtful of design as a thermos. So kind of in the briefest concept, or the kind of highest level concept, you have a basic minimum functioning thing that must meet the requirements, and that's kind of where you can think of like a baseline or code building. And then you have something that's a little more thoughtful in design in terms of air sealing and thermal protection and durability and quality. So that's just a very high level concept about passive building. And then I briefly, before we dove in, wanted to talk about what a passive building standard does. And I'm glad you mentioned all of that stuff up front, Brett, about the prerequisite programs, Energy Star and EPA and OR Plus. Those are all really good programs that require some quality elements that FIES leans on in terms of moisture design and indoor air quality and things like that that don't necessarily show up in kilowatt hours. They're not things that that passive building on its own can achieve. So I'm going to talk about what it means or what passive building can achieve, but it can't do all of these things on its own just using passive. So you have to rely on those co-requisite programs to ensure a quality building. You can't get that alone by just using passive measures. So the FIES passive building standard requires design for low heating and cooling loads and bills. So that's peak and demand, or peak and then annual, and I'll talk about that a little later. It requires design for low net energy use overall. So we use a source energy metric, and that's also our zero program, which I'll talk about. And then it also requires quality construction, which is this on-site quality assurance third-party verified programs that are ensuring the building is a quality built building. Okay, so just a little bit of history. There's a little bit of, the first kind of experimental homes with passive solar stuff actually happened in the States in Urbana, Illinois. I'm in Chicago, I didn't mention that. So just downstate of here, actually where University of Illinois is at. And that was the Building Research Council, and they kind of came up with this low-cal home. Similar concept to passive solar. And then during the oil embargo in the late 70s, early 80s, Canada said, okay, we really need to take advantage of some of these passive solar strategies to reduce the heating load. And they had all of these kind of design strategies, really more passive solar than passive building, which is important to understand. They were more of a heating dominated situation, lots of solar gain, mass, glass, but they knew super insulation and air tightness and solar gain could help you reduce a heating load, right? They just didn't have like really defined targets, but they had all the concepts down. And then in the mid 90s, those concepts were taken by the FAIS Institute in Germany, or I guess not taken, utilized by the FAIS Institute in Germany that created a pass-fail passive building standard. And what this did is it quantified those passive building conservation measures and said, hey, you need to take these and go to this certain amount of conservation. And that's how you apply those passive building standard or passive building practices. And you can go this far and meet these certain metrics, and that defined kind of what a passive building was. And that passive building standard works really well for passive buildings in Germany, or passive houses in Germany, and was applied for the European climate zones. And then in the early 2000s, our executive director, Katrin Klingenberg, took those concepts from Germany and that passive building, those metrics for Germany, and applied those to a building outside of the US. And she built her own house in Urbana, Illinois. No relationship to the 1970s Urbana, just a coincidence there. And as well, I guess then the FAIS Institute US was formed, and as we continued to try to design to the FAIS Institute Germany targets in the US, problems arose. Different climates, different solutions, and different kind of co-requisite programs and quality assurance in different areas. So in 2015, FIES came out with a climate-specific passive building standard, and since then, this is really applying to North America. And since then, we've refined the standard for FIES 2018, kind of adding a few more elements in there. And then we actually just last night launched FIES Plus 2021. So these are climate and cost optimized for North America, whereas the German passive house, which you may have heard of, is the original targets were cost optimized for Germany. So just a little more on that. There are different passive house institutes all over the world. You can see us in the top left, PHIJP, Italy. You can see a little bit of correlation there in the logos. But there's, different flavors of passive house, but they all rely on the same principles. And that's what I'm going to kind of start with. Okay, so also to just put this in a kind of a zoomed out context, this is the US Department of Energy's high performance staircase. You can see on the far left, we're starting with code, IECC 2009-12, Energy Star, ZERH, the Zero Energy Ready Home Program. And then FIES kind of just builds upon those and goes a little bit further in different arenas to get to a zero building. So we have the ZERH, which is zero energy ready. Then we reduce the loads even more, add a little bit more related to ventilation quality. And then you can take renewables and get to zero. So it's just kind of a natural progression also on the kind of predefined programs we have in the US. Okay, so now into the passive building principles. So there's 5 main principles that we generally talk about, and these principles are trying to achieve 3 different control strategies. So we have thermal control, radiation control, and air control. Thermal control is achieved through continuous insulation, and I'll talk about each of these individually. So thermal control, continuous insulation are kind of that sweater on the building, not the same size sweater for every climate, but a sweater or a coat, or a nice continuous layer of insulation. We have radiation control, which is controlled by optimized windows and solar gains. So notice this is not passive solar. It's not all the gains you want. It's not all south glass. It's really optimizing the window and solar gain to your climate. And that's what the kind of performance targets that we'll talk about are trying to gear you to. There's limits on heatings and also limits on cooling, so that you can't really go too far in either direction. You need to optimize. And then there's air control. So this is achieved through 2 strategies. The first, super important for energy savings and durability, is airtight construction. And then because you seal up the building so tight, you now need to provide intentional balanced ventilation. And then with heat recovery, so you're not losing quite a bit of energy as you continually provide fresh air to the space. So those 2 come in tandem. You really should not do one without the other, especially when you're getting down to passive house levels of air tightness. You need that balanced ventilation with heat recovery. So these are, there's key core requirements to the standard based on those 2. And then kind of as a result of all of this, you're reducing the load on the building, and you have minimized mechanical systems, and often they're simpler as well. Less need for distribution to every corner of the building because of that thermal control. Okay, so just a little bit on each. So the first is continuous insulation. This is a fairly intuitive concept, but really just not just focusing on the construction of an individual component itself, like a wall, but also focusing on how that interconnects with the other components in the building, like the windows, the floor, the roof. So reducing the thermal bridging at connections between components, as well as within, structural framing of an individual component. So you want the insulation to be continuous all throughout the building thermal boundary. And one way to think about thermal bridging, if you're not familiar, is you have a nice sleeping bag, right? If it's cold out, you get in that sleeping bag and you roll over and you feel that zipper. That zipper is a thermal bridge, and that's the kind of path of least resistance for thermal transfer between the inside and outside of that sleeping bag. Whereas, the sleeping bag's really well thought out, but then they have this conductive part that causes discomfort, and buildings could cause condensation, mold, other issues. Another thing about thermal bridging, or I guess shown here in the bottom, is that it provides for more livable space as well, especially in somewhere like this high rise. You can see on the left, they did not thermally break that balcony slab. So the balcony slab goes all the way from inside to outside, and that creates, or basically allows the cold to come in, or really the heat to go out. And what it's doing is it's creating a cold corner, which could have issues for mold, or it's just cold and you can't use that space. So when you mitigate that thermal bridge or provide that thermal break, you're now creating kind of more uniform temperatures on the inside surface of that building, which again is good for comfort, but also building durability and things like that. Oops. Okay, so air tightness, another really key principle here. The FIES 2018 requirement, AM 2021, sorry, missed that update there, is 0.06 CFM50 per square foot of envelope area. So it's a per square foot of shell area requirement, not an ACH requirement. But it's roughly 5 times lower than the IECC 2015. I think the requirement's the same, 2018 requirement. So it's tight. It's achievable. It's been achieved in hundreds of projects across North America, but it is tight. It's significantly tighter than code requires. Okay, so in optimized windows and solar gain, often, or it's pretty much required to use window frames with thermal breaks in them. And then oftentimes also, at least in climate zones, maybe 4 and above, you're seeing triple pane glass in most buildings. Not all, but most. And also like curtain wall systems and things like that in larger scale or commercial buildings. You're getting into kind of top of the end for the curtain wall systems that are available, triple pane glass and a thermally broken spandrel. So they exist, but it's definitely higher end of the window market. And as I mentioned before, there's also shading strategies involved with this, depending on the building type and usage and orientation and all of that. There's ways to obviously allow for gain when you want it and block it when you don't. Okay, so the balanced ventilation and heat recovery, again, remember, goes hand in hand with the air tightness. And this is basically using intentional openings in the building to provide fresh air in the living spaces and exhaust stale air in kitchens and bathrooms, maybe laundry spaces. So spaces where contaminants build up, you're exhausting, and spaces where, like living rooms, bedrooms, you're supplying fresh air. And it's a continuous thing. And it's going through both heat recovery at the core. So your outgoing air is passing through a core with your incoming air and exchanging that heat and moisture generally, if it's an ERV, an energy recovery ventilator, or just exchanging heat if it's a heat recovery ventilator. And it's also going through a filtration system. So you're constantly providing fresh air, fresh filtered air to the living spaces, which just provides a really, really high indoor air quality relative to something like, what's the next slide here, relative to maybe a conventional ventilation system where you're exhausting from some spaces and then based on pressure differential, air is being pulled in through other spaces, which could be through your walls or your crawl space or something that's not quite as clean as a nice filtered ERV. So it's just a more balanced approach. Insulate your envelope, seal your envelope, and then you have these intentional openings, and then keep the pressure balance in there even. So you have this balanced continuous ventilation. Just provides very good indoor air quality. And oddly enough, I have Mitsubishi on here, but, oh no, sorry, LG on here. But we have minimized efficient mechanical systems. So again, as a result of all of these things, you can minimize the mechanical systems. You're cutting loads in buildings significantly, and you're also cutting the need to create like super distributed systems that might need, I don't know, bring heat all the way out to a window because previously the window was creating a pool of cold air in front of it because it's so low performing. Maybe you can just supply heat and cooling to the interior walls and reduce distribution and simplify the whole thing. Okay, so these next few slides are going to talk about how basically the questions that we went through at FIES to come up with the passive building standards that we use to certify buildings. So I think there's 4 or 5 of them. So this is kind of the first overarching question, was how do you set targets for investments in these passive measures and ensure quality building? So we know we can take all of these passive measures, save energy, and then we also know we need to get elements that ensure quality building. So the result of that is to create this passive building standard that kind of encompasses all of that. So FIES 2021 and also the previous versions, 2018 and 2015, are performance-based passive building standards with prescriptive requirements. So I'm going to get into exactly what that means, but it really, the core of the passive elements are what FIES is adding, or the FIES standard is adding to those existing co-requisite programs that Brett mentioned in the beginning. Okay, so the main certification requirements are space conditioning targets, so that's heating, cooling loads, air tightness, on-site quality assurance testing and inspection. That's a combination of, well, it's basically those third-party co-requisite programs, Energy Star, EPA, and Plus, Zero Energy Ready Home, and ensuring those and in combination with some FIES requirements on site. And then net source energy. So what's the overall impact of the building? And the top three are pretty much identical for every certification you achieve with FIES. And then the bottom one, the net source energy, the total impact of the building, varies based on if you want to go for what we call core or zero. So I'll talk through all of that, but I basically want to walk through how the different targets were arrived at for these different kind of pillars of the standard, and then what that means in terms of a zero framework for a zero certification. Okay, so the top one, space conditioning targets. The question here was like, how low can and should you go with these passive measures? Like technically you could continue to add insulation to wall assemblies, roof, your floor. You could get the best windows that exist, and you can continue to save money and reduce loads, right? But like eventually you hit this kind of point of no return. And we tried to find that cost optimum spot. So how low can and should you go with these measures? So our target setting methodology was essentially a cost optimization study. We studied various residential buildings, the sizes shown below there, all the way from I think a 200 square foot tiny home up to a 10-story high rise. And essentially what we did is we set up different packages or upgrade packages for these buildings. So you start with a code baseline and you say, okay, I want to increase my wall R value, my roof R value, decrease my window U value, add balanced ventilation with various levels of heat recovery percentages, change solar orientation for some of these. So you have all these, the passive building principles or measures we saw in the beginning, and you basically crank those from 0 to 100, right? So you can go really far or not at all. And what that does is it took these buildings, essentially, it created all these different scenarios or all these different combinations of implementing those passive building strategies. And what we were looking for was the one that saved the most energy for the least amount of cost. And so the cost is a combination of upfront costs. So those upfront costs and conservation measures, maybe you had to pay a little bit more for the ventilation or for the better windows or the insulation or the air sealing. But you also save the most energy over time. Or sorry, the combination of cost is ongoing and upfront. So we have the upfront costs of the measures as well as what it costs to operate the building. And we looked at a 70-year lifespan for the buildings. So what you see on the top right over here is the minimum cost curve. So that's that curve at the bottom, and that's where you have the most savings for the least amount of cost, which is the y-axis. So that red circled point is kind of the optimum point for that specific building, which is just one of hundreds used in the optimization. And basically what it said is you can get source energy savings around 43% relative to the baseline for actually less cost than the baseline itself when you combine upfront and operational costs. And what that looked like for this specific building is kind of on the bottom right. Benchmark building, it basically did what passive building can do, which is reduce heating loads significantly and also maybe apply some conservation strategies to other things like hot water systems, lighting, large appliances, things like that. A couple of things about this optimization is the window selections were constrained based on comfort. So we didn't let it pick all the way from code minimum to the best out there. We said, okay, you can't do code minimum, you have to do a certain U value based on FIES's comfort requirement for windows. So that was locked in. And then we also forced them to air seal up to the FIES requirement, the 0.06 CFM 50 per square foot. And it also had the ability to pick a tighter air tightness, which also or often happened in the optimization. They said, okay, that's a really cost-effective measure. So this study in setting these targets is really the core part of passive building. This is what passive building strategies can do to buildings. And what arrives from that is essentially space conditioning targets for both annual and peaks. So we have targets for annual demand, which is the total heat or cooling that must be delivered to a space to maintain a set point. So it has nothing to do with the system delivering it. It's just, I need to keep this space at 70 degrees, so this is how much I have to deliver to that space. And the passive building principles are what influence that. And then you have the peak load. This is what's used to size mechanical systems, and this is basically what do I have to deliver to the space at the peak condition. So for passive building, it's the average of the worst 24 hours. For other programs, it might be the 99 percentile. Depends what load scenario you're sizing. But again, it's not influenced by mechanical systems. These values alone are only influenced and only met achieving passive building strategies. And then what that ends up looking like is, with all those different scenarios, basically we studied all ends of that spectrum and building size and climate, different unit densities, different occupant densities, because these influence internal gains and internal load. We came up with different targets for all of the North American, well, all of the climate zones in the US and quite a handful in Canada. So there's over 1,000 locations with different targets. And the way to kind of see what that would be for your building or your project is to use our performance criteria calculator. So all of the optimization work that went into this is kind of packaged up in this tool, where you come in and you select your project type, location, you put in the building size, which we use envelope to floor area ratio as a kind of proxy for that. So the shell area versus the floor area, which is also kind of a metric for compactness of the building. And then it also depends on the dwelling unit density in the building. If it's residential, that's not a factor if it's not. If it's non-residential, and then also the occupant density. If it's in residential mode, it'll ask for bedrooms. Otherwise, it's just total occupancy. And you can see in the red box that the space conditioning criteria then populate for this specific building and this specific climate. The source energy criteria populate below that, but we'll get to that in a bit. So, in case I didn't say it, these are pass-fail metrics, and all 4 of these must be met. So you have the heating over the course of the year, the cooling over the course of the year, and then your peaks for heating and cooling. And what this, again, does is it helps you, it guides you in each kind of direction by placing guardrails on all of these. So these targets came from the results of that optimization study. How did the buildings that were at that optimum point perform in terms of these 4 metrics? And then we use basically statistical analysis to figure that out for all the climate zones and all the variations of building types. Okay, so that is the main part of what passive building has added to the certifications, or the certification. It's really a lot about meeting these space conditioning criteria, and that's really the unique part of passive building. Okay, so next question is, what's an acceptable level of air tightness based on building durability? So we know building air tightness saves energy, but also we need to make sure that the building we're building is durable and long lasting. So our technical committee, and a few of them are with Oak Ridge National Lab, they did studies on kind of, it's called what's an acceptable level, which basically it's like how do you try to prevent the building from long-term rot or durability issues. So they figured out kind of an acceptable level that could go through a clear section of the building envelope. And then I won't get into too many details here, but basically this number comes directly from that durability study. So it's 0.08 CFM 75 per square foot of envelope area, or if you track that back to CFM 50, it's 0.06. There is a slightly higher allowance for buildings that are non-combustible construction. The durability concern is not quite as great for those buildings without the framing members that are durable to, vulnerable to mold or rot. So it's slightly higher, 0.08 CFM 50 per square foot, or 0.11. And again, this is part of a hard requirement for the standard. You must pass this result through both pressurization and depressurization tests for certification. You take the average of those 2, and that must pass this threshold.
Lisa, can you clarify non-combustible as all electric? Is that another way of saying it?
No, not all electric. Sorry, this is related to the envelope, the building envelope. So basically anything without wood framing.
Thank you. I see non-combustion and I'm like, oh, there's where my mind goes.
Yeah, that word I guess is, and we will talk about combustion in the other sense too later. So yeah, thank you for pointing that out. That is, yeah, things with non-wood framing. Okay. And then kind of the third pillar is what are these other quality related items that are valuable but don't show up in the energy model? So I've kind of touched on these, but this is our really key part of the standard, which is using these great defined government level programs for other quality related items. So the Energy Star, Zero Energy Ready Home, and EPA Indoor Air Plus. And we kind of add a little bit to that with the blower door testing, the ventilation system balancing and commissioning. But this is achieved by the rater and verifiers. So these are professionals that we train. The rater is built on kind of the HERS rater designation. The verifier is more of a big building aspect to it. But I can't stress enough that this part of the certification is super, super important to actually getting the building that you're designing, actually achieving what you intended to design. They're testing to make sure everything that's actually in the plans is what's in the field. And they're making sure the systems work, they're making sure everything's commissioned, they're making sure the air tightness is met. Really, really, really critical for the building success. Couple other requirements. We have a requirement for window comfort. So basically there's a maximum U value per climate that you can use for your window. And it depends on the height of the window as well. The larger or taller the window, the tighter that requirement gets. You need to make sure the window also has limited risk of condensation. So generally, if you're meeting the comfort requirement, that's not a problem. Generally, we see issues with the condensation risk on like a curtain wall, spandrel, or something like that, where the frames really aren't too great. We also have moisture control and assemblies that we limit or kind of review. So that's kind of looking at your hygrothermal properties of the assembly. So what's the vapor profile of the assembly? And we have certain things that just pass by inspection for FIES certification and certain things that require a deeper look or a deeper analysis. And then we also look at moisture control at unavoidable thermal bridging. So something like that, one of the thermal bridging slides at the beginning where you saw that balcony slab, that corner at the interior of the balcony slab could create a temperature cold enough to grow mold. And what we do is we make sure, okay, if you have that thermal bridge and you can take the heat loss, fine. We make sure that there's not actually going to be mold growth there through kind of a simulation and therm to see what that temperature is at like a critical test point or critical condition. So even if you have thermal bridging or you can't avoid thermal bridging, we make sure there's not going to be a risk of mold growth at that corner. So these are kind of supplementary requirements, again, that don't really show up in an energy model, but are super important to make sure that the building is actually a quality building. Okay, so the last one is related to source energy. So when do you switch basically from conservation, I think I lost a word there. When do you stop with conservation and turn to renewables to offset source energy? So again, we talked about how you can continually add insulation or improve your windows or get a better HRV or ERV, get more solar gain or more optimized solar gain, but eventually you're pushing too far. And you can get the best heat pump out there and the best fridge out there, whatever, everything that goes in the building. You can get the best out there, but eventually you hit a roadblock or you hit a stopping point with conservation. And if you're actually trying to get to zero, you have to turn to renewables. And maybe it makes sense to go a little bit before buying top the line everything to turn to renewables. And it depends. So this is a question we tried to figure out and answer with these tiers. Okay, so source energy, just for those that aren't familiar, is essentially just a better proxy for carbon emissions because it takes the energy or the site energy used at the building, so what shows up on your utility bill, and multiplies it by a source factor based on the fuel type. So for natural gas, that is a 1.1 source energy factor, and for the FIES 2021 standard, for the US crude grid electricity, that's 1.8. Previously it was 2.8 in the 2018 standard. The 1.8 is actually projecting into the future out to a 2050 outlook based on some work that NREL's done, basically to try to get a more futuristic look of comparing using grid electricity at your building versus natural gas. There's quite a discrepancy before the 1.1, 2.8, but the building is going to be used more than just today, right? More than just the day you're designing for. So we need to look at kind of what's closer to halfway through the building's life to really assess the impact from a source energy standpoint. And Canada has a slightly different, higher number, and that reflects today's outlook. They don't have the same kind of future grid data that we have in the US. Let's see, what else do I want to say here? The graphic on the right here kind of shows the level of source energy that you can achieve with FIES. So you've got your historic baseline, and then you have your core program, which I'm about to introduce, which is taking that baseline and using all those passive and active conservation strategies. So again, the 5 core strategies in the beginning, as well as equipment efficiencies and things like that. And this is your core target, and that's a conservation target, that yellow target. And it's remaining on the building boundary. Maybe a little bit of renewables, I'll talk about that. But it's in the building boundary, it's just creating a really good building. FIES 0 steps, or I guess expands outside of just the building boundary. So you still do everything you did with core, but now you can expand outward of the building boundary and use both on-site and off-site renewable energy to get to 0. So another way to look at this is we have a baseline building. We use all the passive building strategies plus some other active conservation strategies and get that really good building at core. And then we can chart all the way to 0 by adding on-site and off-site renewables to get to 0. This is net zero operating energy. We're working on things related to really taking time of use into account, more of a grid citizenship, understanding that different kilowatt hours of the year aren't all created equal, and a net accounting, doesn't really address that. But this is where we're at right now in terms of the certification standard. The budgets here, are the total limits for residential buildings are per person, and for commercial are per square foot. For core, which is that core main conservation level, the residential limit varies. It's a sliding scale based on, again, unit density and occupant density. And this is really because that you don't want to penalize a smaller building for having more people in it. Or it just needs to scale to appropriately set something that's a conservation target and not something you need to use renewables for. It's a per person limit because you don't want to penalize something that's a denser building with more people, like a 500 square foot apartment with 2 people in it versus a 5,000 square foot built single family home with 2 people in it. That's going to look better from a square foot perspective, but worse from a kilowatt hour per person per year. So we're trying to limit the very big buildings with few people in them. The 0 target's always 0. For non-residential buildings, it's per square foot again. This is kind of a base number, but there's additional allowances for process loads on a case-by-case basis. So if there's something inherent to the way the building is functioning, those must be kind of added to that allowance. This is for all the main things in the building: heating, cooling, general lighting, ventilation, things like that. But then additional allowances may be added to that core target. And then again, 0 is 0. So when we look at the 2 different levels, there's different ways that renewable energy is treated. For core, basically the only thing that counts is on-site renewable energy, and it only counts what you can use while it's being produced. So that means, like, if you're, let's say you have a kilowatt array of solar array on your roof that is producing over the course of the year what you're using over the course of the year, you only get to account about 1/3 of that to actually meet your core source energy target, because a lot of it's going back to the grid. You're only able to use about 1/3 of it while it's being produced, and no offsite renewable energy counts. So core is supposed to remain at the building level. Again, renewable energy not required to meet the target, but is a viable strategy to meet the target. With the zero certification, it's mostly aligning with the ASHRAE 189.1 Appendix J and the way Architecture 30 looks at this, which is basically saying that on-site renewable energy counts the most and the least is the renewable energy certificates. So every kilowatt hour of on-site renewable energy counts to offset 1. And then in between that, the other offsite strategies like directly owned renewables, community renewables, virtual power purchase agreements, things like that that aren't on your site, but are still have quite a bit of regulation to make sure there's additionality and things like that. Those count at 0.75. So every one of those you get offsets 0.75 at your site. And then renewable energy certificates, basically every 5 of those offsets 1 at your site. So they're just weighted differently, basically based on the value of the different types of renewable energy. Okay, didn't realize this was animated. Okay, so talking about kind of the getting to zero with the passive building baseline. So this zero standard, kind of the hierarchy here is we want to make sure we have quality, health, durability. We implement our passive building strategies and we get our active conservation strategies, and then we've hit core. We got on-site renewable energy and off-site renewable energy. So this is kind of the way the FIES zero standard is set up in terms of hierarchy. You must do the bottom to get to the top. And the bottom strategies are more important to implement first than the top. So that's kind of the way that the program works. Some of you might have heard of the Zero Code, created by Architecture 2030. I think this is a little bit outdated. They have a slightly newer standard reference, but they basically say design an energy efficient building, use all these strategies. They use 90.1 2016 as the minimum standard, and then they say, okay, do the rest of the energy needs with renewable energies. So this is what you use based on 90.1, and then everything else, just get that same amount of renewables and you're at zero. And we pretty much follow the same framework, except what we're saying, instead of just ASHRAE 90.1 at a certain level or code, is we say push further, go to core, that's the conservation target, and then address the remaining building needs with renewable energy. So we're pretty much in line with the 2030 challenge. And one way that was really great to see that was represented was in this a recent Chicago Architect magazine article that pointed out only one firm in the greater Chicago area met the 2030 challenge, and that was one of our longtime certified passive house consultants, Tom Bassett-Dilley Associates. His firm was meeting the 2030 challenge, and they're a firm that's committed to doing all passive building. So they're perfectly in line, and the people that are using these strategies are, aligning and meeting that 2030 commitment. So it was really great to see kind of the synergy there. If we look outward from the building boundary, this is kind of for a whole separate presentation, but it's important to understand that there is a ripple effect of conserving on site. As we're thinking about transitioning to a full renewable energy future, we're not only replacing the existing infrastructure, but we're also introducing a lot of intermittent variable resources that need additional transmission to get to places and also need storage to make dispatchable. So essentially, if we can reduce the building load on the left, we can reduce the amount of renewables needed to offset that. We can reduce the amount of storage needed to make that renewable energy kind of useful or dispatchable, and we can reduce the amount of transmission needed to get that to and from the locations that it's needed. So there's a ripple through the whole system outside of the building boundary that's not included in the optimization studies, but it's something to really be considerate of, especially as we're all trying to get to a more clean electric grid. We have to understand that there are challenges associated with more renewable energy. So there is a big difference between this top set of row homes and the bottom set, even though they're both net zero on paper. The way they're impacting past their building boundary is quite different. So we're really aiming or targeting for that lower set and striving to show that conservation is a really, really key part of kind of facilitating more renewable energy into the electric grid. Okay, so then one new question that we asked with the 2021 standard, or that we kind of addressed with the 2021 standard, is after passive building metrics are met, what other provisions support building decarbonization? So here we are back at combustion. So looking at combustion and electrification. So we have the FIES core, again, that conservation strategy. Combustion's okay, but electrification readiness is required. So this basically means anything with combustion, water heater, space heating, cooktop, dryer, basically it. You need to have the provisions in place or the infrastructure in place that it can be replaced with electric appliances, maybe upon the next maintenance cycle or in the future. And then we have, I'll skip down to 0, no fossil fuel combustions allowed with the FIES 0 program either. So you can do core and do combustion, but if you want to go all the way to 0, no combustion allowed. The core prescriptive I will get to later, but also no combustion allowed. I'm going to pick up my pace just a little bit. So something new with the 2021 standard is there's a requirement for electric vehicle readiness, essentially based on the number of parking spaces. So for each dwelling unit, if parking is required, 1 EV ready space is required. And this is really similar in concept to solar ready, right? Like a dedicated branch circuit running the conduit and letting that, basically the cost of this is very low to implement during construction, but a lot more expensive if you're trying to implement it later on, when you actually want to add the electric vehicle charging. So we have the EV ready requirements and then EV capable spaces, which are doing a little bit less than EV ready. I won't go too deep into those. Okay, so the certification process, or actually, yeah, we'll dive into that. But first, kind of numbers just to get you a scale of where we're at. Roughly 7,200 units. This is a little outdated, I apologize. End of last year-ish, and roughly 8 million square feet across the US. And the graphic on the right kind of shows geographically where that's at. A lot of heavy concentration in the Northeast and West Coast. So we're seeing it everywhere, but really a lot on the coast. And a lot of that's driven by incentive programs that are in different areas. The certification process is 2 parts. The first part is a design review, a pre-certification. So the certified passive house consultant submits the project, and then it's kind of a back and forth review process with FIES. And this should all be happening while the project's being designed, not while the project is being built, because the pre-certification process is kind of intended as consulting and points out red flags that are happening. And you know, if it's already built, you can't address those, and then the project could it could have issues, worst case, or it could just not be certified because it can't pass based on either modeling errors or, again, you know, hygrothermal red flags, other issues like that. So you want to get your design pre-certified before construction starts. And then there's the final certification. So the project's being built and there's the on-site testing from the raters or verifiers that is happening throughout the construction process, reviewing insulation installed, doing preliminary and final blower door testing, ventilation commissioning, and basically making sure that the project designed is actually what was built. And if not, pointing out what the delta is, and we true up the energy model. So the final energy model must still pass. A little bit about the team. The certified passive house consultant on the far left is the energy modeler for the project, and they're really the head person during the design phase. We have the certified builders, which are involved in the building phase, maintaining quality and oversight during the construction, air sealing details, things like that, like making sure the building is being built at a quality level, you know, moisture control. And then we have the rater or verifier, depending on the building size. So the rater, small scale, verifier, large scale, required, hired during the design phase. They need to be hired during that phase. You need to have someone in place to be there throughout the construction schedule, generally 4 visits minimum. And they're the ones, again, finalizing everything and shipping it back to FIES for the final certification. The performance targets, we talked about the annual demands and peak loads and source energy values are met in an energy model. So we use WFI passive energy modeling software. It focuses on showing compliance with those 4 targets. down here in the bottom right, the demands, the loads, and the source energy. So it's built specifically with various levels of the FIES Plus certification program within it. And then we have a quality assurance workbook for single family, multifamily, and non-residential projects, which, depending on the prerequisite program per level, have those kind of built into them, as well as the FIES requirements. And this is what's used by the rater and verifier. And just a quick note on the modeled performance. These are different project numbers across the bottom. And then the blue is what was modeled in WFE Passive, and the red vertical bars are what was actually measured. So some projects have multiple years of data. We're kind of seeing things all over the board, right? Some are really consistent modeled versus measured. Some are pretty far off. In the grand scheme of this chart, the site EUI is on the far left, so kind of the highest we're seeing is 35. But what's really important here are these dashed lines in the middle. And what this is showing is the average modeled building throughout all of these projects. The average site EUI was about 15.6, and the average measured was 16.7. So the delta there is only 7% modeled versus measured, and these are different project sizes through different climate zones, different occupancies as well, obviously. So the models basically are working, and that we're really happy to see this.
Lisa, can you confirm that that's actual utility data, like a full year's worth? And is that normalized for weather variances?
No, so the models were not changed for weather. They're using your certified model. So we didn't change the models for occupancy.
Sorry, not the model, the utility bills.
They're not normalized. No, it's actually what was used in the building.
Okay. Yeah. Interesting. And so what is that, a 90% accuracy or so?
Yeah, it's 93. Yeah, it's pretty close. Yeah.
Fantastic. Thanks for clarifying that.
Yeah, no problem. So we have a whole separate presentation on this, but where we kind of do try to true up the energy models with the climate data and the actual occupants in the space, and they get pretty darn close. But obviously you could design a 3-bedroom and 1 person lives there, or 6 people live there, and that can make this fluctuate a lot, or set points, or years with polar vortexes, who knows. Okay, okay, I can try to jump through this pretty quickly. So people often ask us, like, okay, what does this look like compared to a code building? So I compared a Chicago case study with IECC 2021 with our FIES 2018 standards. So again, we just launched 2021 last night, so I didn't have a chance to update this yet. But this is kind of what it would look like. The top part is the passive measures, then you have the kind of mechanical systems or active conservation measures, and I'll kind of talk through this. So with IECC 2021 on the left, if you're looking at the thermal envelope, you've got a little more, almost double in the walls for the FIES building. You've got whole slab insulation. The window U values are about half of what they would be for IECC 2021. So again, the same air tightness, about a third, a fourth of what it's required for IECC. And then for the ventilation strategy with the FIES building, you've got your balanced ventilation with 75% efficient heat recovery. The mechanical system performance, both of them have heat pumps. So we have slightly higher HSPF for the FIES building, same SEER, so that's heating versus cooling efficiencies. Water heater efficiencies, we've got an electric kind of standard water heater with IECC and a heat pump water heater for the FIES project. And then the appliances and lighting all stayed the same. They're all the Energy Star median values. So what we land on here is an EUI before renewable energy, so whatever you use those conservation strategies to achieve, of 21.5 for the IECC and 16.4 for the FIES Plus building. Again, this is before renewables. And what that looks like really here is still a 24% reduction in energy use in the building, even though you're comparing to one of the latest and greatest codes. So there's still room for improvement. I think everyone knows this beyond codes, but still quite a bit. Quite a bit of low-hanging fruit that can be implemented and save a lot of energy there. Probably the biggest delta comes from the combination of the balanced ventilation and the air sealing. Those are, if you can only go from IECC to FIES on those elements, do those two elements. Maybe the wall insulation and windows, they're not going to get you as much in the energy savings or in the air quality realm. So I think that's really still the biggest delta between the codes and what FIES is promoting here. Okay, so I'm going to very briefly talk about a new approach, a new alternate approach for FIES Core, which was launched last night. So we had that, remember, the FIES Core and Zero. So this is your conservation, this is your good building, staying on building site approach. So this is kind of the hierarchy here. It's limited in scope. So the first question you'd have to ask if you wanted to take this approach is if you're doing a single family duplex or townhome. If you're not, boom, you're over to the left. You have to do the energy modeling with WFI and you're in the performance path. If it is single family duplex or townhome, you can continue on the right. And if you're going to not do WFI passive modeling, no, then you get down to core prescriptive. And I'm going to talk through kind of what that means very briefly. You can also see the Revive on this slide. The Revive is essentially the retrofit version of each standard. The end goal or end performance targets are the same as the core and core Revive are the same in terms of what you're achieving in terms of energy performance in a building, but where you're coming from is different. So Revive has a different kind of designation. So you can also see here the two levels that combustion is allowed versus not allowed. Core prescriptive, not allowed, the X and Zero, not allowed. Okay, so the core prescriptive basically prescribes elements in all of these different areas. So at the high level, we have different scope limitations. So only certain buildings qualify to use this prescriptive path. And then once you weed out those, the green boxes are essentially the sections of the standard that address the passive building elements. So you're looking at requirements for solar protection, for air tightness, for heat transmission, and opaque and transparent components. Mechanical ventilation requirements, compactness requirements. So the building can't just be the craziest shape. We limit that. And then moisture risk limitation from both an opaque assembly and also transparent assembly perspective. So it creates requirements for all of these different kind of passive strategies. And then there's also requirements for active strategies, such as mechanical system efficiencies, as well as lighting, appliances, and hot water. This is basically all I'm going to get into today is what the scope is. So the scope for the prescriptive is single family detached or attached. It must be that, or you have to take the performance, which is everything prior to these slides. Is all talking about the performance, which is really the core, the standard way people think and achieve passive building up until this date. And probably will remain to be the dominant one moving forward. This is just a limited scope of buildings that can follow the prescriptive path. There's a limit on floor area per bedroom, so essentially you can't have those McMansions I was talking about. No fossil fuel combustion, no jetted tubs, indoor pools, or natural gas fireplaces. Along with this kind of program checklist, you can kind of see in the screenshot on the right, which contains all the nitty-gritty details of the program. We have this online tool called the Snapshot. Essentially, if your building falls within these scope limitations, you can go into this snapshot and see basically, okay, here's my building, here's my size, bedroom, stories. Again, it's my single family building. And this is roughly the levels of performance you need in these different categories. So compactness, solar protection, my envelope, R values and U values, mechanical ventilation, and mechanical systems. So it gives you just a rough feel for what you need. It's early in design thing. It's not used for compliance. The checklist is used for compliance, but it's supposed to give you a rough feel of, okay, if I wanted to follow this prescriptive path, these are the project and climate specific requirements I'd have to follow. Everything else is more of what we call a static requirement or a universal requirement. It applies to all buildings. These are the ones that are sliding scale. And especially the heat transmission section, a lot of these are built from the same optimization studies that we use to build the performance targets. We're just building targets kind of at the other end of the line, right? So our performance targets came from putting certain combinations of these into buildings and then seeing how they perform. we took a step back and said, okay, what were those combinations, and can we figure out what those requirements are? If we limit the scope quite a bit to that single family, yeah, maybe we can figure out what's required, and we have to limit the compactness. Like, we need to get this as close to the study buildings and cost optimum that we can, and then we can probably put numbers on those. So that is what the prescriptive standard is achieving. There's a free webinar that talks all about this next Thursday. I put a link in the slides here. So please attend if you're interested in that. It's going to be an hour all about that standard, how it's developed, what the requirements are, and all of that. Okay, I've got resources now, Brett. I'm wondering if you want to do questions, or if you'd like, this probably will take about 5 minutes to go through. I know I'm a little over already.
Yeah, no, that's fine. And I think why don't we get to the questions, and then kind of after we get through those, as you head out, you can kind of go through the resources, and they're in the handout too for everyone who wants to kind of read through them. So I shared that on there. If you don't see it, let me know. But yeah, let's get to those questions. Before we get to the questions, just real quick, I want to just remind everybody who's got to go that you're good to go. You don't have to stick around. You are approved. I know some people worry about that, but we want to get to all your questions and have a great conversation. And Lisa said she can stick around too. So let me just quick pull this up here. And can you see my screen?
No.
No?
Oh, there it is.
Okay. And that's your title slide. But quick, yeah, check your spam for your certificate. The email is your certificate, so please check your spam from customer care at gotowebinar.com. That you'll get your CU. The FIES code number is hiding in that, and so you should be seeing that, within an hour with the survey details in there. For those of you watching this in the future on demand, please take your 10-question quiz with an 80% passing rate, and then you'll get your certificate and your FIES code. After that, you can check it out on our Thinkific platform on our website. Otherwise, whatever other site you're watching this on, GBCI, follow the instructions there. Nope, don't need that. And then a real quick, as those questions are coming in, thanks to our top tier sponsors, Build Equinox, Mitsubishi, and Ream for helping us achieve better buildings, all electric indoor air quality, and all of our other sponsors, our board of directors, our volunteers, and everyone who allows us to do what we do. And again, just another reminder there that this course is approved for FIES CUs, and it is all self-reporting, so we won't be reporting it for you. So make sure to go through the self-reporting. So yeah, a lot of questions here. I want to go back to one at the beginning for a second, and that is, and James has been great online answering the questions, but I want to make sure there's some really good ones that I want to bring up. And the question is, how architects cannot control the occupancy. So can you just clarify on how occupancy plays a role in Passive House?
Yeah, sure. So there's a couple different factors with occupancy. There's how people want to live in terms of the temperature, the interior temperature set point. So passive building is actually really good at kind of boxing that in a little bit more, because the amount of energy it takes to heat, let's say, a passive building up to 80, let's say that people want to be at 80 in the winter, it's a lot less when it's a passive building versus when it's a code building. That's when you're going to see a huge swing in the heating, right? Because it takes a lot more to heat a code building up to 80 than it would a passive building. Same with cooling. So in terms of temperature set points, of course, you can't control what they're doing, but you are kind of minimizing the range of what you'll see when doing a passive building. For appliances and lighting and plug loads, that's just kind of the Wild West. You can install a certain amount of lighting, but if it's not enough light, in a residence, people will bring more. So that's not something that's, generally, it can't be achieved through passive measures. It's a hard nut to crack, I guess, is the shortest answer I have on that.
Okay. So it's true that your occupancy is counting bedrooms and not the amount of people in there, correct?
Correct. So we're certifying essentially the building as designed. So it's
Right,
bedrooms plus one is equal to the occupancy that we're modeling for. We
right.
found that's been fairly true, but of course there's discrepancy to that. But when you're kind of certifying a building and you have to use kind of, you have to use standard assumptions for a certification. If you
Mhm.
wanted to do real estimates for your building outside of the certification, of course, revise things as you know, but have to standardize a bit.
Um, Here's a great question, and I'm going to expand on it a little bit. Where does Passive House come into this growing demand and need for prefabricated walls, or even, frankly, modular housing? Is it possible to work with modular manufacturers to get Passive House certification? Are there big barriers? Are there any success to that?
Yeah, I think there's barriers and there's success. I wouldn't say there are success stories of that. There are certified modular housing. There are certified, well, we are currently building a kind of a certification panel program to try to get more manufacturers kind of pre-approved for this type of certification so that you're not kind of going into it blind as a designer. But it's absolutely possible. I wouldn't say there's more barriers than standard construction. Maybe the biggest barrier would be the air sealing, making sure if you are using a panelized system, making sure the air sealing thermal bridging at the junctions between them is paid attention to.
I wanted to go kind of on that note, what happens if you know, somebody at the end tests out and achieves all the results that Passive House is looking for, but failed to do all of the pre-planning and designing? Because we see it all the time. We see projects who didn't go through, if from like LEED, they want to have you do design shreds and all these LEED meetings, and it's like, I don't have time, right? I just got to build and get to the next one. We have a housing crisis. We have a housing shortage. So what do you say to people who say, I don't have time for all your design time, Passive House. I'm just going to build it, test it out, and if it meets it, can I get my stamp?
Yeah, the short answer is yes. If it is your first one, I would really, really, really recommend against it. Even if it's not your first one, we've seen essentially the certification is providing another set of eyes. I would like to say we don't have quite as many elements of like design charrettes and little kind of tangential things like that that other programs have. Like we're kind of to the point. Like, is your energy model passing these things? Do you have moisture requirement risks? Like, are those met? Are you meeting the pre-arch programs? Like it's a little more pointed than maybe other programs, and that's intentional. But the quality assurance during design is really important. However, if you can achieve what you needed to achieve and you can pass all the on-site rigor required, so all of the on-site testing and requirements for blower door, ventilation commissioning, balancing all the on-site inspection of insulation, all of that, if you did all the on-site stuff, you can come back, yeah, and submit the energy model for the building, and we're still going to certify the building, assuming it meets all the requirements.
So, there is clearly all of these different entities. And the big one, of course, is there's, Passive House International and then FIES. And sometimes you're always trying to figure out, which program someone is talking about. And then, when you ask them, it becomes very clearly obvious, where they're at. Do you see some sort of merger between everyone where we can kind of just focus on Passive House and forget about which program it is, or is there any conversation there? It sounds like there's some more collaborations.
Yeah, actually, it was in one of the, I swear it was in one of the slides, maybe it's in the resources. So what is happening right now is an ASHRAE passive building standard, standard 227P is in progress, and that's taking together people basically from all over the world to come together to create an ASHRAE validated passive building standard that it will be in code adoptable language, and it'll take these principles and it'll be climate specific because it's a worldwide standard. But basically it is a merger of all the concepts. I wouldn't say that there's any sort of clashing in terms of concepts between the Passive House Institute in Germany and the US. It's just one is more geared toward Germany and one's more geared toward North America and climate specificity because of the challenges that the US sees in terms of Alaska to Hawaii, right? That kind of just was not addressed in what we saw with the German standard, and that's the reason for the optimization.
Yeah, that makes sense. And I see a lot of FI projects, and that's because I mostly work in climate zone like 5 and 6 I mean, that's pretty much what their zone is, correct?
I would guess they're more of like a like a 4C,
Oh,
5C.
close to five, yeah.
Um,
Yeah.
yeah, not as much cooling, dehumidification.
Mhm.
I mean, it's a longer conversation.
Right,
The
right.
target, it's really hard to compare in a short amount of time, but it could work for heating dominated climates, but it's not the same cost optimized kind of background built into it as the North American standard.
Sure. Makes sense. Um, so obviously, if you say passive house to anyone, one of the things they're gonna say is, well, I can't afford triple pane windows. Now, you said triple pane windows, but you talked a little bit about these minimum U values. So tell me a little bit about, if there are double pane windows that can meet all the requirements, or you can use because you are performance based. So if you use performance targets, is it possible to build without triple pane windows?
Yeah, so we set maximums on U values based on comfort for the climate. So you can absolutely start your design right there. And if that maximum U value can be achieved in a double pane, fine. It's a balance. So if you do the absolute worst or highest you can do for a U value, then you're just going to have to make up with it in other places. You're going to have less windows, or you're going to have better performance of your opaque assemblies, or better performance of your heat recovery system, or it's all a balance. It's all a balance of those passive building strategies to meet those targets. So
Yeah, and thanks for correcting me. I try to speak
that's okay.
more in R value for windows because I think it makes more sense to people. So then
It
I was
does.
like, there's a R value floor in that case then, right? So,
Yes. R
but
value
yeah,
floor, U value
yeah,
roof.
yeah, yeah.
It's good. Yeah.
Um, so natural gas, obviously it's got a little bit of a higher number or more favorable number in your system than electric.
Mhm.
Was all these reports we're seeing about these massive leaks through the distribution line from cradle to cradle, or what I guess cradle to gate, cradle to sky. Are those factored into your data?
So that is part of the source energy factor, the 1.1. I think that's the biggest part of the source energy factor, because most of the source energy factor for electricity is the conversion of a fuel to electricity and then the transmission, whereas natural gas is just the transmission, since the conversion happens on site. So is the 1.1 perfect? I don't know. That is what's in the EPA Energy Star portfolio. So those are nationally published numbers that we didn't come up
So
with on
you're
our
just
own.
using the EPA's
Mhm,
data set. Yeah, okay,
mhm.
that makes sense. Um, let's see, some more questions coming in, and thanks again, James, for helping tackle some of them. I want to see if I can bring some of these here to light. Um, what about people who want to do this but kind of get their feet wet a little bit? Is there any kind of modeling tools they can use or trainings for them? I know you're going to speak a little bit to that, but
Yeah, probably I guess I would say the lowest hanging fruit is a feasibility study. If you're a designer, or if you want this done for your project, if you're a building owner or someone that's about to create a building, we have the feasibility study, which there's a slide on that in the resources, but it's essentially a quick preliminary study of the building, either as designed if you have a design, or if you just have the shell, that's even better, early in the design, better. So we can give you some guidance on what it would take to bring this building design or some variation of that building design to meet these standards. That's the easiest snapshot level, or the prescriptive snapshot, now that I say snapshot. But that's really only if it's a single family home.
okay, so prescriptive is only. When you say feasibility study, does that mean they need someone? I mean, like a lot of times folks like to kind of just do things on their own a little bit, get a little sense. So is that a study that they're using a tool on your website, or is that something they need to reach out to someone about as they're
Yeah, that would be a FIES service. I mean, the training is the best thing to do on your own. There's also the guidebook, which is a combination of kind of requirements, but also some design guidelines or recommendations. It's a mixture of requirements and recommendations. Attend the FIES webinars. We have a ton of free webinars with content out there. It's kind of the best I can think of on your own.
Yeah, no, thanks. And I know you're going to address some of that. Here's a great question, and I know you spoke a little bit to the future of the grid
Mhm.
and the electric conversion, which is great. But the fact of the matter is, our climate zones are changing too. And
Mhm.
so how are you factoring that in or planning to factor in the fact that our climate zones are going to shift?
Mhm. So we thought about actually updating this FIES 2021 standard to use future climate data, but this version of the standard didn't. We extended the optimization in terms of building size and kind of the factors that went into it, but we didn't rerun all of the optimizations. So if we use future climate data, essentially we just adjust the targets to meet that future climate data, and it would arrive in a very similar design. So it's going to take a full overhaul of the standard with future kind of optimized files with future climate data. So we have that climate data, and you can estimate, okay, this is my building, and if I put in the future data, this is how it's going to perform. But the targets also need to be updated to reflect that. So that could be a focus of the next iteration of the standard. It was just not a main focus of this 2021, which was more about getting all the way to zero, figuring out the right ways or ways to get to zero, and also expanding. So it's emissions down, scale up is kind of the tagline. So how do we force or get more people to be able to get to zero, incentivize electrification, decarbonization, and also scale up? So the addition of this prescriptive path was a huge leap for this version.
Great. So I had overheard you say, you can now use solar to meet core in your energy modeling. Is this new as of this standard? Could you do that before?
You can do
And
that.
anyway, if so, how much solar on average do you usually need to meet the goal, and does it vary by climate?
Yeah, good question. You could do that before. You shouldn't need any, is the short answer. You can use it though if there's some other constraint in some other way that you need to. So you can't achieve it through other other active conservation strategies, then you can use solar, and only again like a portion of it counts. So
Like
it's a coincident
10%,
production. Sorry?
20%, like 10%, 20%, like how much?
Depends. Once you get all the way to net zero, so that's probably the most you're ever going to put on your roof, it's about 30%.
Okay.
If it's
Well, I'm
smaller,
sorry.
it's more.
But you had said you don't have to be zero, but you can still use solar as part of your equation, correct?
Yes. Yeah,
Okay.
you don't have to be zero. That's just the one I know easiest. So the less you put
Right.
on your roof,
Hmm.
the more of it that counts.
Hmm.
If you keep adding it, less and less counts. So it's kind of like a fixed number that counts in terms of kilowatt hours per year offset.
Hmm.
And so even if, let's say, I have 5,000 kilowatt hours per year
Hmm.
produced by my solar,
Hmm.
maybe only 1,000 of that counts. Even if I put 10,000 on my roof, only 1,000 still counts. So that percentage is variable, but the amount that's actually offset in terms of absolute kilowatt hours is static, is the same
Hmm.
number.
Yeah, that's great because one of the biggest, the second besides the windows, the second biggest, concern I hear is that I got to pour all this money into R80 insulation. I'm just using an example, right? Like people just sometimes they don't know what they're saying. They just say, I have to put it into this R80 insulation or this 20 feet of slab foundation. They're like, I just want to put it in the solar and be done with it. So it sounds like there is opportunity to do that.
You can't, no. So
No,
I'm glad you
okay,
said
maybe
that.
not.
You still have to meet the space conditioning targets. You still have to meet the heating and cooling demands and loads. That's one pillar. The other pillar is how far you go with other strategies like equipment efficiencies, and that's where solar can compete. So if they're like, oh, I don't want the hyperheat. I can't afford the hyperheat. I'm just going to get a solar array that can offset a little bit more instead of getting the absolute high-end heat pump out there or something. That's where solar can compete. It cannot compete with passive measures.
Great. Thank you for clarifying that. Yeah, that
Yeah.
I didn't want to leave the wrong impression there. So,
No.
um, let's see. Well, speaking while we're on this, where can, especially in the source zero side, where can on-site storage play a role? Like there's new ideas coming out, like the idea of what we call net zero summer, where,
Mhm.
you know, okay, we can't, being totally net zero makes no sense because in the winter we're going to need to rely on the grid. We have really no choice unless we're going to buy a lot of batteries and solar, which is just not practical for most. So the idea is, I think people are using batteries to sort of pretty much stay away from the grid in the summer, especially up here in this climate, and you know, unless there's an emergency or something. So can you actually count that? Because it sounds like the solar you send to the grid really doesn't count, but that
Right.
could you use that stored battery solar?
Yep, exactly. So for the core level, that would essentially increase the utilization percent that we were just talking about. So if it was 10% before, maybe with storage it's 20 or something.
Mm-hmm.
So yeah,
So
it can
then in
affect
that,
that, but not the zero. It doesn't affect the zero certification, which is still an annual what you produce versus what you use.
oh, okay, so it'd be more for the core. You could incorporate
Yep.
some battery to
Yep.
extend the solar a little bit more. I'm trying to think of where I was, what my next thought was there, but that's all right. Let's see. Yeah, we got quite a bit of. Oh yeah, can you talk briefly to renovations?
Yeah, sure. So essentially the same standards that I outlined here apply for renovations. It's our Revive standard. The performance targets are all the same, except there are allowances on a case-by-case basis if there's existing structural thermal bridging. So those space conditioning targets would be adjusted just slightly to account for that thermal bridging. Some of the co-requisite programs, if they don't apply to retrofit programs, then we would not require it. So basically we lean on where they draw that line at a retrofit to, as if we require that or not. But everything required for FIES, like the air tightness, ventilation balancing, all of that is the same between a new construction and Revive project.
Great. I'm trying to see. There's quite a bit of other questions here, and I'm trying to see which ones we can try to get to right now. Well, why don't we? Why don't I look at that? Why don't I kick it back over to you?
Sure.
And you can tell us a little bit about the resources and the classes coming up, just so people can, you know, figure out what they should do best to take the next step. So let me turn it over to you.
Yep. Okay. Let me get everything back to my other screen here. Okay. So you can see my training screen?
Yes.
Okay. So the first slide is just talking about our upcoming training. So we've got upcoming training for our various professional certifications. These are all switched to online, so a lot more convenient for people to take these. Our main, where I'd say our most popular training is in the top left, the CPHC. That's intended for architects, engineers, building designers, sustainability consultants. That's our longest training too. It's a two-part training. There's a phase 1 on demand, which is kind of rolling access. And then phase 2 is 24 hours live, split over 8 days. And we basically have that coming out on like every 6-week basis. So you can see the upcoming dates below. There's one happening right now. One starting April 12th, May 10th, June 7th. So again, it's a clear, a pretty predictable progression. So you finish your phase 1 and then you register for a phase 2 session. We have our, sorry? You can say anything.
Oh, sorry.
No, you're okay. The next thing we have is the CPHB, Certified Passive House Builder. This one also has some pre-recorded content. You register all at once, but you still need to watch that. I think it's about 10 hours on demand prior to the 24 hours live sessions, again, split over 2 weeks. Same thing, those are rolling out every 6 weeks or so. So we have a class coming up at the beginning of April, May, and in middle of June. We also have a rater training. This one's happening probably the soonest, in a few weeks. This also, same kind of format as some on demand, at your leisure. About 8 hours that you go through, and then you have 9 hours of live instruction. And then the verifier. So again, the raters for the single family context. The verifier for the larger multifamily or non-residential is same format as the rater. the 8 hours on demand and then 9 hours live. And that's starting in early April. And we will continue, like these are the ones that are, coming up. We'll have another rater and verifier probably late summer and then maybe again in the winter. So there's usually a couple of those per year. The top two are on a 6-week-ish rolling basis. And then another training, we've been hosting more online WFI passive trainings. We just finished a WFI passive for beginners, which we'll host again in probably a couple months. Really successful, big class. We have a single family pro course coming up, which is essentially if you've used the software before, but you want to get better at optimizing or modeling single family. This is coming up, 4 hours per day, split between 2 days at the beginning of April. The beginners course works the same. It's a 2-day, 8 hours total. We're also working on getting dates out for a therm training, which is modeling thermal bridging. I believe it's going to be middle of April. Check back on our website under Become a Professional. There's all the different trainings on the left side of the screen. And then working on a WFI passive for multifamily specific and WFI passive for commercial buildings. This I just wanted to point people to make them aware of it. This is our certification guidebook. A new update's coming in a few weeks, so maybe wait for that one on FIES 2021. But great resource. Again, it has everything from design recommendations to certification requirements, energy modeling protocols. If you did want, there is a free version of WFI passive you could download, and if you wanted to try to step through that on your own, you could use the outlined information in the guidebook to help with that. We also have other design guides and a policy roadmap. So we have kind of specific sites for multifamily and commercial buildings. If you're in one of those realms, multifamily.fies.org or commercial.fies.org. And on there's these free design guides, really great references, show case studies, show some cost data, and then there's a policy roadmap also for people that might be trying to incentivize passive building through policy or other measures. And here's the slide on a feasibility study. There's also a page on both the multifamily and commercial sites about this. But basically, this is a feasibility study that FIES offers, or any certified consultant could offer it. Really, it's just doing a quick energy model of your building and showing where it's at in terms of meeting the performance requirements. Depending on the size, from a single family up to a high-rise tower, the cost varies, but it's fairly low cost, and it's turned around in about 2 weeks. And what we give you back is a completed WFI passive energy model of both what you're designed, or a baseline if you're saying this is your baseline, as well as one that's meeting the passive building standard. And it's just one iteration or one combination of measures that work. So like we were talking about, maybe you want, you can't use windows with the U value better than 0.2. So that's locked in. That met the comfort requirement. Now you can, mess around with all the other opaque elements or the ventilation efficiencies or things like that. So there's tons of different combinations. FIES provides the one that we would at a high level recommend, but it gives you one combination of things that would meet. It gives you a comparison versus code or a certain baseline that's optional, and you'd have to provide what baseline you wanted that to. And then there's a 1-hour follow-up call with the team, which we found to be very helpful. We review the findings, and I'd say in my mind, really the most successful, or really the biggest takeaway from feasibility studies for teams, is that it introduces elements into the conversation earlier in the design, things that wouldn't usually be talked about. And then generally, even if you're not going to do a certification, you can tackle some of these issues or things earlier in the design and actually have that conversation earlier in the design. So we found that teams really find that valuable to start to talk about these elements that maybe are kind of a second thought or a later on in the design thought, and just don't get the attention up front that they need. Here's some samples. These are larger scale projects that we used to only, or the feasibility studies that came in the beginning were much larger scale buildings, but now they're kind of all sizes, all different types. Maybe it's a unique type of building. And a lot of them actually turn out to be certified projects. So most of these are certified projects now, or at least in the certification process, maybe half of them. But I'd say we have at least a 50% turnover from a feasibility study to certification. So it's pretty good. Oh, here's the ASHRAE slide. So yeah, ASHRAE established a passive building standard committee. Again, that's in progress. I think the first draft is supposed to be released late in about a year. So it is a slow process, but it's been in the works, and I'm pretty optimistic about what the result will be. This is kind of a conclusion slide. I think we've talked through all of this, but basically we're targeting low operational carbon, low upfront cost and investment in envelope and systems, thermal comfort, and then also getting the actual measured performance that you're expecting from your model. Okay, so that is officially the end of the slides.
Great. Well, I do not see any other questions, but where can people reach out to you or anyone over at Passive House if they want to learn more?
Yeah, so we have a couple emails. Maybe can I put them in the chat, or they're kind of easy.
Yeah,
if it's about training, let me see, I lost the chat. Oh, it's popped out. Okay, if it's about training, you can go to training@fies.org. It's pretty straightforward. If it's about certification, building certification, go to certification@fies.org. That'll actually go to James, who's been answering your questions here. Well, it's only going to you. I'm sorry, Brett.
I'll pass it on to everybody.
Yeah, no worries. And my email is lwhite@fies.org. If you have specific questions or anything about this presentation, or I can definitely direct you to the right person at our organization to answer your questions.
All right. Well, we're going to go ahead and wrap up. Thank you all for sticking around to engage in more conversation. And thank you so much, Lisa and the Passive House Institute US for hosting this and for all the work that you do. And, you know, again, we love doing our webinars. We're going to keep doing webinars, but we do want to see you all at some point in person again. So with everybody's help to do everything you can to stay masked, stay in when you don't need to go out. And we can use building science and many of these principles to help us, not just with COVID, but beyond COVID, with ventilation, filtration, humidification. We know we need to clean our air in our buildings to make us safer and healthier. So let's spread that message about that so we can reopen, get back to work, get back out there. Stay well, stay safe out there, everybody. Thanks. Goodbye.
Thank you.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.